Hey calculus students, we're going to start talking about one of the more conceptually difficult concepts in all of multivariable calculus, and that is the concept of doubles and triple integrals. They're conceptually difficult. They're difficult because they take a lot of work in terms of computation, and that's just something that just happens. But two, from a conceptual perspective, it's kind of hard to think about what it means to actually have a double or a triple integral. But what I'm going to try and do right now is to kind of try and simplify that. And so I'm going to go back to functions of a single variable. And so let's remember what integration was when we were working with functions of a single integral. When you were working with functions of a single integral, what we did was we would take our function, and the value of that function was our y value. And if you remember, that meant it was the height. It was the height of the function. And then what we would do is we would multiply that by our delta x. All right, by delta x, and we'll take a look at that in just a moment. We'll write it down. By delta x, and then we would just basically take a height times that delta x, and we would add it together in various different ways. With Riemann sums, it was basically just, we were looking at rectangles. We did trapezoids. There were some midpoint things that went in there. But basically the idea was that we would take these rectangles, and then what we would do is we'd make the delta x smaller and smaller and smaller and smaller, right? Until what we were doing is we're basically, the way that I always thought of it was we were just painting, right? It was like we're accumulating, stacking up tiny little slivers underneath this curve until we got the entire area of the curve. And that ended up being our integral, all right? And that kind of fundamentally informed everything that we did from an integration standpoint. So that's what we're thinking about when we start thinking about in two dimensions, basically a function of just a single variable. Now let's think about it from a perspective of a function of two variables, and that's where the double integral is going to come in, right? We now have two variables, so I'm going to have to integrate twice, okay? But what does it even mean? So what we're going to be thinking about is we're going to be thinking, okay, on the one hand I have my function, which is a function of two variables, and I'm going to integrate along my x-axis, or parallel to the x-axis, really. And that's going to be like my delta x. Okay, it's going to be my delta x. It ends up being my dx. I make each one of those smaller and smaller, and what I'm basically doing is accumulating along that x-axis, and that gives me one edge, like 2 dimensions of what's going to end up being a volume. Then what I've got to do is I've got to imagine I'm going to move it. Okay, I'm going to move my viewpoint of it. It doesn't actually move. I move my viewpoint, and now I'm going to move along that y-axis, or parallel to that y-axis. And parallel to that y-axis, I'm now going to be integrating with respect to y. And so now I've got a delta y. Okay, I'm going to go with respect to y, and I get a delta y. And that gives me I'm now going to be taking those, I've got that, basically that figure that I've been working with before, which was my two-dimensional slot, right? That was the integral that I just took that gave me a two-dimensional sphere. And now what I'm going to do is I'm essentially going to now stack those up until I get an entire volume. Okay, so I start out with, I've got my curve, right, with respect to x. I basically take my integral, create a two-dimensional figure, right? Like basically, if you kind of imagine like a plane, or a curve on a plane, and its area underneath that. And then what I'm going to do is I'm going to stack up those kind of planes until I get my entire volume. And that's kind of the concept that we're going to be working with as we think about taking a double integral. Essentially, a double integral is we're going to be finding the volume over a region, okay, for a particular curve of two variables. So let's talk about this concept of value. So let me actually just start out with let f of x equal y. And we're going to look at that two-dimensional example. And here's our y-axis. Okay, you remember we have a curve here. And essentially what we did, we had a delta x. Okay, we got this delta x. And then this would end up being, we call that f of xi star. Okay, and we did that several times. Got another delta x. Got another delta x. And so essentially what we would do, right, is we'd actually add up, we added these areas. right? We had another f of x, we'll call this f of x2, f of x3, right? So on and so forth until we ended up, we had the end of our interval. So this was a, this was b, that's the end of our interval. And we added these up. And then, if you remember, we would take the limit as essentially delta x goes to 0 of each one of these, right? This summation. It was a summation of our f of xi's times delta x, right? And that ended up giving me my integral. Now, all this means is that we're just taking the sum of all the boxes. Okay, that's really all it is. And then we made the boxes really, really small, right? And so, like I was saying, the concept that I always worked with it was like, okay, so here's my figure, right? There's my figure, and now instead of I'm making, I'm painting it with these individual strokes, right? So they're getting really, really close together. They're very, very thin, and then by the time we're done, we filled in the entirety of the area, and we get the actual area. Okay, and that's our concept when we're talking about integration in 2 dimensions. When we talk about integration in 2 dimensions, that's kind of like what we're dealing with, right? This is like delta x gets small. It's really small. So we're going to get kind of a parallel here when we talk about integrals in now 3 dimensions. Okay, so let's just give that a second. So I'm going to introduce some notation, and I get r. R is going to be a region, not R. R will be a rectangular region, and we write it as this. We're going to write it and say A to B cross C to D. Okay? And let me actually just generate what this might look like. Say, for example, if we were to have R equal to, and this is 1, 1 cross, and let's go 2, 2. Or, excuse me, negative 1, 1 to negative 2, 2. And so this is essentially, this is going to be the x interval. So on my x-axis, what I'm going to do is I'm going to go from negative 1 to 1 on the x-axis. And this is going to be my y-interval. And so I'm going to go from negative 2 to 2. Okay? Negative 2 to 2. And so essentially, this is going to be that box that we're looking at there. And that's going to be the region. So if you notice here, it's basically everywhere where x is between, x belongs to negative 1 to 1, okay? And y belongs to negative 2 to 2. That's going to be my rectangular region, okay? Now, what this is, though, is this is going to be the domain. Or, well, it's not really the domain. It's the region over which we're integrating. Excuse me. So these are going to be like the bounds for our integration. And so we kind of want to imagine what we're going to do is that we're going to kind of set this down. Okay. So if we set it down in 3 dimensions, right? We've got, here's in the y direction, there's negative 2 to 2. Let's say that that's that distance. And then here's 1 to 1. And what we're going to be doing then is we're going to be integrating over this region. Okay? And if you think about it, it kind of makes sense. Because a curve, let's say, for example, we were pulling a curve of some sort in here. Okay? Pardon my curve sketching. Let's say, for example, that that's the curve. Okay? And what we would do with this curve then is we would basically say, okay, well, I'm going to mark everything that's in this curve over that region. I am absolutely astonished at actually how good I did that. That is stunning. You never know under pressure how well you might do something. But there it is. That's the idea. So we've got this curve, and over the top of that curve, right, there's the region on the curve. Right, that's, excuse me, over the region negative 1 to 1 and negative 2 2. Okay, so basically we're only looking for this volume. Okay, we're going to be looking for the volume here. Okay, that's underneath the curve within that region. Right, so you kind of imagine it's just a weird looking box. Kind of that's the deal, right? Okay, So we introduced that notation, and what that notation is going to mean for us in terms of our integration is we are looking for the volume under the curve, or under the surface, really, actually. It should be under the surface and over the region R. And that's one of the concepts that we're going to be working with here. Okay? So there we are. So we've got this idea of a region. Now we want to imagine is what's going to happen when we actually go and find that volume underneath the surface under that region. So let's imagine that what we've got here, let's pull out a vertical trace. Right? And so if you remember, it's a vertical trace, and this, let's say for example, we've got Z and the XZ plane. All right, or something that is actually parallel. It's really parallel to the XZ plane, but let's just, for the sake of instruction, that what we're looking at is something that's on the XZ plane. And so, if you imagine you've got this surface, and let's say you can look at the surface kind of like sideways on, and you'd say, okay, well, let's say here's our negative 1 to 1. There's that region, or that part of the region. Okay, and our surface might look something like this on negative 1 to 1, right? Now it's going to look different on based upon y, right? So the y value is like, it's just going to look different based upon the y value. That's totally true. But let's just say that if we're given here at, say, for example, y equals negative 2, this is what it looks like. And so what we would do is we just we're like, okay, I'm going to integrate, and again, I've got delta x, right? My delta x there. And I kind of, again, I've got basically these Riemann sums. And I'm going to take that area there, right? So we're going to find that area. And we'll imagine that what we're doing is we're going to find the area. And then, so I'll take a snapshot here. See if I can do this now. Okay. So again, what we said before is here I am, okay, that's at x equals negative 1, and we've got the surface kind of looks like this over x equals negative 1, actually at negative 2, so it's this set, and we say it looks like this there, okay? And so that's what that area is going to look like at that point, right? Again, not the greatest. That's actually the 2. Ha! We'll just pretend, negative 2. So going from, right, negative 1 to 1 at y equals negative 2, we get like something that looks like this, okay? Around there, all right? Now, what we're going to do is we're going to say, okay, well, I'm going to stack these. And this is a little hard. This is going to be much harder to draw. But like, if I want to imagine, I'm going to just kind of like stack these. Each one's going to look kind of different. But I'm going to stack them kind of like I would, like the equivalent of, kind of putting these areas up against each other. And I'm going to do that all the way down until I get to, let's say that this is what it looks like when y equals 2. Okay? And so I kind of just, I stack until I actually generate that area. Or excuse me, I generate that volume. So it's like, okay, to get an area, you're stacking one-dimensional figures, and then that turns it into 1D figures, and it turns the figure into 2 dimensions. So it turns it into 2D, and then to get our volume, what we're going to do is we're going to stack areas. We stack areas now until we get a 3D figure. What we were doing here is we were multiplying by delta x. What we're going to be doing with to get our volumes, actually, if you kind of notice, is we're going to be stacking delta y's. We're going to be multiplying by delta y. So we're basically going to take an area. So we'll take the area, and then we'll multiply it by delta y. Okay? So our area was a height times delta x, and our volume is going to be an area times delta y. Okay, that's the basic idea. Now there's a little bit more to it because the figure isn't smooth all over the place. It's not going to look exactly the same. You change x, you change y, you change the entirety of the figure. But our basic idea here is that we're going to essentially first create an area, right? Okay, by multiplying by either delta x or delta y. We'll talk about that in a bit. And then we're going to stack those up in order to create a volume, right? And then that'll end up being 3D. Area is 2D, a volume is 3D. So what this is going to allow us to do, that kind of like that theoretical thing, is it's going to allow us to think about the properties of these integrals. So what we're going to do is we're going to assume that the functions f of xy and g of xy, they're going to be integrable over a rectangular region. Call it R, S, and T. And we'll have S and T, R. And S and T are subregions of R. Subregions meaning like if this is all of R, okay, here's R, this might be S, this might be T. They're parts of it. Okay, that's what we mean by subregions. And assume that M, little m and big M are real numbers. The sum, f of xy plus g of xy, is integrable. Okay, so that is that we want to make sure that this sum, if each one of them is integrable, then both of their sums is integrable. And what that means then for us is that if we take the double integral of their sums over an area, over a region R, then we can basically just add the volume of the regions add the volumes of the regions separately, right? Okay, so this is basically integrate and then add. And so oftentimes that's going to be a lot easier for us. Or it might actually be really kind of handy from a theoretical perspective. So it's like integrate then add. We can add then integrate, or we can integrate and then add. Okay? Now, if c is constant, then c of f of xy is integrable. So c is some constant or scalar. And basically what that means is you can pull a scalar out. The double integral of c of f of xy dA is equal to c times the double integral over r of f of xy dA. So this is pull a scalar out, right? And we do that all the time. And that's something you can do when you're working with double integrals as well. Now, suppose that r is equal to s union t. And that's what's happening right here in this sequence, right? S union t equals r. That is that s and t put together gives us all of r. There's nothing left over, right? They're the full area, okay? And s intersect t is equal to the empty set. And what that means is that, except maybe an overlap on the boundaries, that's basically saying that we're not like, we're not doing something like this, where we've got r, okay, here's r again, and here's s, and then here's t, okay? Right, here's s, this is all of s, and then t is all of this. That's a non-negligible overlap, right? So we can't have that. That can't happen. More something like this, okay? Right there, no overlap. And what that allows us to say is it says, okay, well, then what I can do is I can break up R into the region S and then to the region of T. Okay, so I can break up S into the region of R. I can break up R into S and T. So this is break up the region. Now, fourth, if f of xy is greater than or equal to g of xy for xy in R, then we're going to have that their double integral of f of xy dA is going to be greater than or equal to the double integral of g of xy dA, assuming that we're over the same region R. Basically, it's that inequality, the inequality holds, right? And that's going to end up becoming kind of handy for us in the theoretical world. Now, let's take m being less than or equal to f of xy less than or equal to m. So basically, f of xy is bounded. That is, f of xy is bounded below by little m and above by big M. Then what that tells me is that this is, so this is a, you want to imagine m is just a value, and if we multiply it by the area of the region R, that's going to be less than or equal to our integral, okay, or a double integral over that same region, and which is going to be less than or equal to big M over that same region. So essentially, and again, this is going to become something more theoretical, what you're going to imagine is you're going to imagine, okay, so here's my surface, or let me actually bring my surface a little further down. Here's my surface, here's my region, okay, there's my region, there's my surface, all right? And so we're looking for, right, the area of this whole thing right in there, right? Okay? That's what we're looking for, excuse me, the volume. We want to know what the volume of that is. Well, if you imagine that you've just got, now you've got M is this value down here for Z, okay? And we go out and we find this volume here, and we'll talk about that more, but like we go out and we find this volume right in there, okay? That's going to be less than the volume of our region, okay? Because it just is. I mean, you can just see it. Makes sense, right? And if I take a value that's above it, let's say I've got big M here, well now what I'm looking for, I've got, here's that region, and the volume, not the straightest of lines, the volume of that region, excuse me, is now all of this. It's all that stuff in there, okay? And you can tell that that volume is going to be greater than the volume of the region of our surface as well. So basically all this is doing is it's saying, okay, we can bound the volumes. So this is bounding of volumes. Okay? And that's going to actually come in pretty handy too from a theoretical perspective as well. And finally, number 6, in the case where f of xy can be factored as a product of a function g of x only and a function h of y only. So that is that when we have, so say for example, I'll give you an example of this. If we have f of xy equals x squared y cubed, okay, then this actually is going to end up being equal to x squared, right, times y cubed. And so we would say that g of x is going to equal x squared and h of y equals y cubed. Right? That's an instance where we can factor f of xy into a product of g of x and y only. Then over the region R, so this region, whatever the region we're looking at, the double integral can be written as, and so this is going to end up becoming really handy for some theorems that we're going to be working with later on. It's going to say, okay, you know what? What I can do instead of figuring out the double integral is I can figure out the single integral, and I could multiply it by the single integral for x and multiply it by the single integral for y. Okay? So this is basically kind of like factoring, or the way of thinking about it is factoring. Okay? So we're going to see those, and we'll probably see them a couple of different times. You want to kind of, feel comfortable using them. I don't think you're going to need to memorize them, but as I show them and as we work with them, you're going to want to know, you're going to want to kind of like identify them and be able to work with them. So I'm going to break up this conversation into 2 parts, but before we finish up this part, what I want to do is I want to say, okay, so now that we've got all this kind of stuff that we've been working with, now what are we going to do with it in order to actually go out and solve or find the values for integrals? And so what we're going to do is we're going to do something called an iterated integral. So we've got to assume a, b, c, and d are real numbers, and we're going to define an iterated integral for a function f of xy over this rectangular region R equals ab cross cd as the integral from a to b, c to d, f of xy dy dx is going to equal the integral a to b, c to d, f of xy dy dx, okay? Or b, we'll also do the integral from c to d and a to b, f of xy dy dx equals the integral from c to d times the integral a to b, f of xy dx dy, okay? So what you'll notice here, a couple different things, is that we can either do it in the form dy dx, or we can do it in the form of dx dy, okay? And you'll notice that a to b is our region for the x's, okay? So the x is on the outside, and so a to b is also on the outside, okay? So the order of your integral is going to matter. The order of your bounds and we'll call it, let's call it D, let's call it DC. Okay, DC, right, could be X or Y, right? Matters. They have to be in the right order. All right, so if I do dy first, because I'm going to do inside first, if I do dy first, okay, then what's going to happen there is I'm going to have my bounds for dy on the inside, okay? So you basically think of it as inside, inside, outside, outside. So we're going to do that. All right, so we've got an integral with insides, and then we'll have an integral with outsides. All right? Doesn't matter. Well, it doesn't always matter. Most of the time, it's not going to matter whether or not you do dy first or dx first, as long as you put the bounds first. Okay? What we do need is we do need to make sure that that we're continuous on whatever region that we're looking at for both x and y. Right? That we're actually inside of the domain for the function. But if that's the case, then pretty much we can do inside and outside. And we'll talk about that. We've got a little formula that we use that will help us to dictate that. Okay? So we got inside, inside, outside, outside. All right? So like, let's take, for example, we'll do an example here. Something quick and dirty. All right? We'll do, say, for example, the integral from 1 to 6 and then 2 to 9 of the square root of y, x squared, dy dx. Okay? And so when I'm looking at something like this, I say, okay, well, notice that the y's are on the inside. And so since the y's are on the inside, I'm going to integrate with respect to y first, right? So I'm going to start by treating x as a constant. By the way, what that kind of means is that if you kind of think about this, it's like I could basically say, okay, 1 to 6, and then we'll make this 1 over x squared times the integral from 2 to 9, square root of y dy, okay, then the dx. So then I'm just going to integrate with respect to y first, okay? So I'll go do that, and that's going to then be 2/3 y to the 3/2 evaluated from 2 to 9, okay? And then we're going to be multiplying that by 1 over x squared, and then at some point in time, we're going to integrate from 1 to 6 dx. So I go in, I'm going to do exactly that. I've got 1 to 6, 1 over x squared, okay? And this is going to be 2/3. All right. And our y's, that will end up being 9 to the 3/2 minus 2 to the 3/2. And dx. And so that's going to equal the integral from 1 to 6, 1 over x squared. And this is 9 to the 3/2, so that's going to end up being 3. That's going to be 2/3 times 27 minus, and then that's going to be 8 square root, so 2 root 2 dx. So what that's going to then give me is that's going to end up equaling, let's pull out the 2/3, we'll make this 2/3, the integral from 1 to 6, and this will be then, that's going to be 27 minus 2 root 3, 27 minus 2 root 3, or 2 root 2, times 1 over x squared dx. And actually I could just pull out this part too, because it's just a constant. So let's give it as 2/3 times 27 minus 2 root 2 times the integral from 1 to 6 of x to the negative 2 dx. So notice now there's no y's in there anymore. We've turned them into constants, and since they are constants now, they can actually just be pulled out. Okay? And so now I've just got to go and evaluate x to the negative 2. Well, that's going to just be negative x to the negative 1, evaluated from 1 to 6. We'll multiply that by 2/3 times 27 minus 2 root 2. And this will then equal 2/3 times 27 minus 2 root 2 times negative 1/6 minus negative 1. And we'll go plug that into our calculator. And when we do that, we get approximately, or I got approximately 13.4287. And that actually ends up being the value for our integral. So let's kind of look at the process again, all right? It's involved, but conceptually not that bad, not that hard, okay? You just want to think to yourself, okay, what is this process that I'm doing? How am I going to go about doing this process? If you can kind of think through the process, then everything gets easier. If on the other hand, it's always how do I do it, this is going to end up becoming a lot harder. So what we look at is we say, oh, okay, well, if I notice that the dy is on the inside, so that means that I'm going to integrate with respect to y first. So I've got the integral from 2 to 9 of square root of y dy, and I just pulled out 1 over x squared, okay, because why not, right? Okay. And then we will go out, we integrate. What do we get? We get 2/3 y to the 3/2. It's a power rule. All right, and I evaluated then from 2 to 9. So I actually did the evaluation before I went in and I did anything. Okay, so I went in and I evaluate. And so once I've evaluated, what I get now is I ended up getting this. This is going to end up being 27 minus, like I said, 2 root 2, right, times 2/3. And this is just a constant. I know I didn't evaluate the constant, but that's okay. So what did I do? Well, I said, you know what? I can take the whole constant out. Whole constant out. And now notice there are no y's, there's no dy's in there at all. Now all I have is just dx's and x's, and that means that I can just take the single integral with respect to dx. So it's going to be 1 to 6 x to the negative 2 dx. And there we are. Okay? So, once we go through, we integrate that, evaluate at our bounds, in this case negative 6 and 1, and we just evaluate, figure out what our integral is. And there it is, 13.4287. Perfect. All done. Now we do have an alternative method. Remember, we've got 2 to 9 and the integral 1 to 6, and we've got then the square root of y over x squared dy dx. Now if you remember, one of the things that we do have here is this is one of those functions where in fact we can factor out all the x terms and factor out all the y terms. So we can make g of x equal to 1 over x squared, and we can let g of y equal to the square root of y. Okay? Hey, that's great. So what does that mean? Well, or excuse me, we'll call this h of y. H of y equals the square root of y. Well, that means that we can actually separate out. Outsides are the x's, so we can make this 1 over x squared from 1 to 6. We got the integral from 1 to 6, 1 over x squared dx, plus the integral from 2 to 9 of the square root of y dy. And that'll then equal, well, or not plus, but excuse me, times. Remember it was times? Times. So that's going to give me negative x to the negative 1 evaluated from 1 to 6 times, and this will then be 2/3 y to the 3/2 evaluated from 2 to 9. By the way, there's our 2/3 again. Remember that this thing here is going to end up being negative 1/6 minus 1, and then we'll multiply that by 2/3 times, and this is then 27 minus 2 root 2. Yep, there it is, minus 2 root 2. And if you look there, that's going to be 2/3 times 5/6 times 27 minus 2 root 2. Go through, put it back in your calculator. What do you get? You get 13.4287. Ooh. So one of the reasons why I wanted to show you that is actually because we've got to start thinking this way. We've got to start thinking about to ourselves, hey, what's the most efficient way of going about calculating these things? And in this case, I can use a theorem that I have there in order to make this an easier integration. All right, so let's take a look at another example. And I wanted to show you an example where we get a slightly different wording for the problem. In this case, we've got a region, and our region's going from 0 to 2, across 0, 1. Okay, so we're going to integrate over r f of x, y, dA. So that's just your general form for the integral. And then we're going to be given that f of xy equals x. So what we need to do is we actually need to be able to go in and generate an integral for this that we can see. So we're going to get the integral from, and you'll notice that the x values are going to be from 0 to 2, okay? And so I'm going to make dx the inside, and then I'll go from 0 to 1, and I'll make dy the inside, and then my function is x. So f of xy is x. I put my x boundaries on the inside, so that means dx goes on the inside. I put my y values on the outside, and so that means dy goes on the outside. And now I want to go in and integrate. Well, it turns out, again, this is again one of those examples where what I can do is I can actually separate this out. I can let g of x equal x, and I can let f of y, or I can let h of y equal 1. Right? 1 is still a function of y. It's just a constant function. And that's going to actually make our lives a bit easier. All right? So if I go in and I separate out my integral, I end up with the integral from 0 to 1 of 1 dy times the integral from 0 to 2 of x dx. This is just going to end up being x evaluated from 0 to 1, and we'll multiply, or excuse me, y, not x, but y evaluated from 0 to 1, and then we'll multiply that by 1/2 x squared evaluated from 0 to 2. And so this ends up giving me 1 times, right, which makes sense, you know, 1 times, and then this will be 1/2 times 4, which is just going to equal 2. And that's the value for our integral. See? A lot easier that way. All right? By the way, we could have gone in and we could have actually done this iterated. Now, I'm going to do a lot more examples of that when we go in and we find, and we do the, you know, the more practical, less theoretical video for this particular section.